Hi, this is the first lecture in our Physics 2 class. This should be watched right after our first class, which we did review. So you may remember um, looking at a review of a lot of mathematics and even some chemistry for the review, and especially vectors. And you're going to see in this first chapter of electric fields why that review was very important. The way these lectures are going to work is as you see to the side, the time, I'm trying to keep these videos kind of short, and so I may stop the video at some point if it gets too long and then start a second video in order to break those up into different videos. So we may not go through the whole chapter in this video. We'll see how far we get. And then depending on how many videos would depend, of course, on the length of the chapters. And so we're going to start with electric fields and go through the electric force and some different things about charges. All right, so let's just get to it so we don't waste any more time. First, we're looking at static electricity, and this is best way to think about this is looking as charge that is not in motion. So we'll hold on. The wants to do stuff on this. Okay, so we're looking at this as static charge, where we are just looking at the combinations of the charges and how they affect one another. But we don't have a moving charge. We'll get to moving charges later on. And so there are two types of charge. We got a positive charge, which best way to think about that is think about a proton. Let me get this to right. Now, a proton is not the only charge that we'll see is positive, and when we get into one of the later chapters, actually I think it's like second to last chapters, we'll see a lot of different charges that are positive, but the proton is the main charge that is positive. We also have, like, for instance, a positron, which is also positive. And then the negative charge, and best way to think about this is electrons. Okay, and a proton and an electron, they will attract one another, and a proton will repel other positive charges, including other protons. And this becomes big when we're looking at radioactivity. But they also attract negative charges. And then electrons and other negative charges, they will repel each other as well. So electrons push electrons away. And it makes a huge importance when you're looking at the structure of an atom. For instance, water has a certain structure, the way it's shaped, because of the electrons pushing away from each other. And then we have a important law that we're going to get into here called conservation of charge. And that is that no amount of electric charge produced in any process is zero. Another way of saying this is no net electric charge can be created or destroyed. So when two charges come in contact with one another, or in close enough proximity where they are affecting one another, they're not going to just produce new charges or eliminate new charges. The net charge has to be the same. We've seen conservation laws, so you should have seen conservation laws in the beginning of Physics 1. We had the conservation of energy. I'm just going to write this up at the top, which will still make a big importance, because it's still going to apply, especially when we get to nuclear energy. And then we also saw the conservation of momentum, which that times will come up. I don't know if it comes up that often, but it will come up. Alright, so let's get down to the structure, kind of an overview of the atoms, just to make sure we have a good understanding of atoms and the structure. So for atoms, we have in the center, this is where all the positive charges going to be, and all the neutral charges end up in the center. That includes the neutrons that are no charge, and the protons that have a positive charge. And it's a solid center that we call the nucleus. And then the electrons are in these surrounding orbits. And right now, we are looking at them as just circular orbits. But later on, we're going to see that they're not completely circular in a sense, and they can be in certain other areas just around the same orbit. But for right now, this is the basic model that we go by for a atom. And these electrons are negative charge, so they are always trying to, in a sense, get to these protons, but at the same time, they push each other away. And these protons, they would like to, in a sense, get in contact with these negative charges, and but they're kind of held tight together. And how tight they're held matters a lot when we get to radioactivity. Now, because the protons are kind of, I guess you can say, stuck in this nucleus, in this core, they don't get expelled easily from an atom. It takes a lot of energy for one of these little protons to end up leaving the nucleus, which we'll see. That's not the same for electrons. Electrons can easily be ejected from an atom, especially if they are on the outer orbit and farther away from the nucleus. What they can just with some energy get enough moment or enough energy and momentum to, get released from this atom. When that happens, we get what's called an ion. And there are two types of ions, and it all depends on the electron with what type you're looking at. So electrons are negative. So when we lose an electron, when electron leaves the atom, you get a positive ion. Reason being is if we have, for the most point, let's just say two protons and two electrons on the outside, that's the orbit. If one leaves, so this electron leaves, now you have two protons, one electron, and you got a positive ion. So this becomes positive. In the same instance, if instead one electron, oops, it's not responding now. Just give me a second. But if one electron enters, you will have three electrons then and two protons, and you'll have a negative ion. So more electrons means that you're looking at negative charge and even higher negative charge. When we do have, sorry, it's writing now, just how it wants. Let's do that randomly. There's little buttons on this pen, and if I accidentally hit it, it starts writing on its own. Alright, so when we have more electrons and we have a negative ion, we call that an anion, and less electrons you call a cation. And this, of course, is all stemming from what we normally would have on a periodic table, as which we'll get into a lot about the periodic table, but hopefully you saw in chemistry. Well, you have a neutral ion. Right. So if you have your periodic table, I will make sure there's one at the beginning of your notes. So you should always be able to go to the beginning and get the periodic table. If you look on the periodic table, you will have different elements. I'm trying to find mine real quick. Actually, you know what? Let me put one up on the screen. So let me open up the internet. I'll put one up on the screen real quick. Best way to find the periodic table, you just Google it. I try to find certain ones with names and easy to read. Sometimes they're not. But the periodic table will come important, so I just go images. In this whole class, we're going to be dealing with the elements. Let me get one with names here. Alright, let me zoom in on this so we can see it better, but not where it gets blurry. Get rid of this stuff. Gotta love all pop-ups. And let me. Alright. So I don't know. I want to be able to see this here. So let me shrink this real quick. Alright. So we have our element fluoride. It begins with an F. This has, let's see, if you start counting from here, 1, helium has 2, lithium is 3, beryllium is 4, and 5, 6, 7, 8, 9. This has 9 electrons and 9 protons based on the fact that everything on this periodic table is neutral. So when we look at one that is fluoride to the negative first, this means that it's missing, or I shouldn't say missing, it's missing, or it has less than less protons than it does electrons, meaning that it, in a sense, it actually has more electrons because it's negative, so it has more negative particles. So the fact that this has a atomic number of 9 always means that it has 9 protons. So Just the fact that it has a -1 makes it automatically an ion. And the -1 means there are more electrons. And how many more means just one. Okay, so I'm going to put 9 here. If it has 9 protons, and protons decide what element it is, so it has 9 protons, that makes it fluoride, which means if it's an ion of -1, it's going to have one more electron, which will make it 10 electrons. Calcium now, calcium's down here, and this would be 18, 19, 20. Calcium has 20 protons, and would normally have 20 electrons. But this is an ion that is a +2. So it's going to have less electrons. And so it has a -2. And so it actually only has 18 electrons. Now, oxygen is right before fluoride, so oxygen has 8 protons. And since, again, it has a -2 up here, it's an ion. It's a negative ion. And so what the negative means, it again has more. I'm going to use E to represent electrons now. You want to see this often. E and negative to make sure it's an electron. It's going to have more electrons. And it's going to have 2 more electrons. And then the hydrogen, that's the very first element on the table, has 1 proton. So it's a +1, so it's an ion. And it's a positive ion. We put positives here. You guys can do this so you know. Positive ion, negative ion. So hydrogen's a positive ion, which means it has less electrons. And it has 1 less electron since it has a +1 charge. And then neon, this is neutral, a neutral element directly off the periodic table. Most of this last column is always going to be neutral. And so that this means it has the same protons and electrons. So it doesn't have any more. And we see we don't even put the 0 up there, we just don't have an exponent when it's neutral. And so normally neon has 10 protons. It's going to have 10 protons still. And it's going to also have 10 electrons. So now the question is, how does an atom lose or gain electrons? And we're going to go through a few possible ways that they lose and gain electrons. I'm going to minimize the periodic table now. We don't need it for right now. I'll enlarge this as well so I can see the time. Right. So first is what we call charging. And think of this as when we're charging by friction, we're looking at contact. And so this is charging by friction, and just think contact, conduction. One object touches another object and moves across each other. And so a good example is taking a steel rod, rubbing wool on it, taking your socks, rubbing them on the floor, even taking your hand and rubbing it along an animal can transfer electrons from one object to the next. And when that happens, one becomes positively charged, one becomes negatively charged. So when we have charging by friction, we have two objects in contact with one another, and they each become charged because electrons are transferred from one object to the other object. So one object will lose electrons, and the other object will gain electrons. And not just some, they will gain the same. So the ones that lose have to go from what's the element that loses the electrons to the element that gains them. There's no other option there. They don't go anywhere else. They go one from the one to the other. So if this rod lost electrons, and say it lost 5 electrons, the 5 electrons will have to go into this wall. Now objects do not stay charged for long, and this is due to water molecules in the air. Think of the fact that even though we can't see it, molecules in the air are other objects that can come in contact with an object and cause objects to transfer electrons. And once the electron's been transferred, when they go to another object, they're usually not permanently there because it's almost like they don't have a home there. They're just visiting in a sense. They're not strictly bounded into that new object. And so water molecules can easily come along and tell them to get lost. And so the object doesn't stay charged. We also have what's called a polar molecule, and water is a big one here. This is where you have your charges from elements combined together, and they're separated where they have certain sides that is negative and certain side that is positive. So this is the water molecule. As you see, there's two H's, H2O. H's are positive, oxygen's negative. They end up with an even zero neutral charge. But they're polar. This side's negative, that side's positive. So if this side gets too close to a positive charge, it's going to be attracted to it. If this side gets too close to an electron, it's going to cause the electron to move towards it. And the fact that this is polar is why these water molecules will pull the charges off random objects when they're in the air. This is also why it's actually good to have Physics 2 in the spring, because we start out with these static electricities while we don't have a lot of humidity, and so it helps. The experiments are actually going to look a little bit better. When we try to do in the summer, the beginning experiments don't look all that well. Right. Now, for since we're talking about contact and conducting, we want to go into a little bit of the difference between a conductor and an insulator. Conductors are usually metal, and they usually contain free electrons. These are electrons that are more loose and on the outside of, on the surface of the metal, what normally is metal, and they can move around, but they can't break away from the surface. And so these free electrons are also called conduction electrons, because they are going to be why metals conduct electricity and they conduct heat better than things that don't have these loose electrons. And so in this case, we have a metal plate and we have a plastic rod. What ends up happening if we move this plastic rod near this metal plate, these electrons are going to be attracted to those positive charges, and they're going to move towards the positive charges, which is going to make this side negative, this side's positive. Because now if all the electrons move there, all the positive charges get pushed away. And actually they are going to want to move away because they're going to repel these positive charges. For a insulator, this allows very small amount of electrical conduction. They're not perfect. And same thing with heat. Heat will get through, or I should say get lost with an insulator. Electricity can be conducted, it's very poor for conduction. And so there are very small amounts of free electrons for insulator. There may be a few, and if there are more than one normal insulator, you'll have what's called a semiconductor, where there's fewer free electrons than conductors, but there are a lot more free electrons than insulators. And two of the most common ones are silicon, which I used in my graduate studies to actually test charges on a semiconductor, and this germanium, which I haven't really ever used. Some things you just don't come in contact with, but they, I guess, are the most common semiconductors. The other way of charging is by inducing a charge. We call it charge by induction, or charging by induction. And we're going to first look at charging by induction for a conductor. And so we're going to go through kind of two processes here. The first one is we're starting with a neutral metal rod, and we bring it close to a charged object. So here we have the hold on a second, let me just check something here. I don't think this picture goes with that. Anyways, okay, so we start with a neutral metal rod. We bring it close to a charged object. The electrons in the metal rod will move closer to the charged object. Since this object is charged positively. And so this is going to create a positive end on the metal rod and a negative end on the metal rod. And so your rod is still neutral, but it's polar. You have a positive end and a negative end. If we were to cut then the rod in two, we will have a net charge. Right, so you kind of draw it out. You have a rod, you get one end that's positive, you make one end negative, and you cut it right down the middle. Now you have two rods. One's positive and one's negative. These two rods still add up together. You don't have any new charges, or you don't have any less charges. Total, the net charge on these two rods together is still the same. It's still neutral. But this one has a charge now of being positive. This one has a negative charge based on how the charges were placed. This is one thing that's going to be different when we get to magnetism, but it's just, let's not worry about that just yet. When you cut this rod in two, because one end's positive, one end's negative, you get two differently charged smaller rods. And so this would be charged by conduction. We use the, charged by induction. We use the positive charged object to cause a separation between the positive and negative charges so we can isolate them, basically. The other way, the other process, is we bring a negative charged metal rod close to a neutral metal sphere. So this is where the picture comes in. We get the negative charged rod, and this sphere is neutral, but what ends up happening is half of the charges, the positive half, go towards the negative, and the negative half goes away from the negative. Then we hook this up to a wire that goes to ground. So what ends up happening is all these electric charges run away and they run to the ground. But then when you disconnect it and you don't allow the electrons to come back, because if you were to bring this metal rod away from this, the electrons will move right back into this and it would be not charged anymore. But if you disconnect it, what you end up with is a positive charged sphere, a negative charged rod. All the negatives will now be with the ground, and so now you have charge induced on this sphere. And so then again, that's charging by induction. You're inducing a charge without actually transferring electrons from one object to the next. Instead, we are kind of using more clever ways of getting a charge. And then the last one before I end this video is charging by induction for an insulator. And again, electrons can move. For an insulator, electrons cannot move freely. You may have a few, but most electrons will not be moving freely. But they can move slightly within their own atoms. So if you think about it this way, think about little rods in this balloon. Well, this is what that looks like. And if you bring it close to something that's positively charged, the negative side will move towards it. And the positive side gets as far away as they can, but they're kind of not able to go too far. And so this is getting more of a charge on one side that is negative, while the other side is kind of, well, the positive charges are repellent. And so you may have one over here, this is negative and positive, but it's only as far as it can move away from your positive charges. And so this would be part of charging by induction and causing the object to become polar. Alright, I'm going to actually end it right before I get to Coulomb's law. So I don't want to go too long in this video. This is the last thing for this electric scope. It's used to detect charge. We, of course, will have other ways of measuring charge, but this is more of an old-time way of doing things. They have two gold leaves, they have an insulator, a metal sphere, and what you do is you bring a charged rod close to the top bulb, and the gold foil strips will become charged with the same charge, and so then they will move away from one another. The principle behind this, though, is used in actual like oscilloscopes that help measure charge. And so that's why it's still technically important. This is used in this. Alright, I will stop this video at 35 minutes, and the next one will begin with Coulomb's law.